Hey physics, Gaga here. Today's topic is going to be atoms and nuclear fission. For the sake of example, we are going to be using a tennis ball as our nucleus. This is a heavy nucleus, for example a plutonium nucleus widely used all around the world. Each second, it has a probability of splitting into two lighter nuclei, releasing free neutrons and lots of radiation in a process called nuclear fission. Although fission of one nucleus releases some energy, in itself it's not very useful for us. After all, we don't have 24,000 years to wait for one nucleus to split. So what can we do about it? Just get a lot of these things. If a released neutron hits another nucleus, it can instantaneously trigger another fission event. If we have enough radioactive material, we can make sure that on average every released neutron hits another nucleus, which can lead to a chain reaction. Surely nothing can go wrong, right? Fortunately, there are smarter ways to do this. With sufficient cooling and the use of neutron-absorbing materials, we can achieve a stable chain reaction when every fission triggers on average one other such event. Kept in control, power plants based on nuclear fission can provide whole countries with electricity with almost no CO2 emission, using just a few kilograms of plutonium or uranium each year. If you enjoyed this video, please don't forget to like, subscribe, or
Nuclear fusion is the process by which multiple nuclei join to form a heavier nucleus, releasing energy as a result. It normally occurs in stars and fusion bombs. For atoms to fuse, the nuclei must come together. However, the protons in each nucleus have the same positive charge, so they will repel each other. There are special conditions to overcome this problem and make fusion possible. High temperature. High temperatures give the atoms enough kinetic energy to overcome the electrical repulsion experienced between the two protons. Fusion requires temperatures of about 100 million degrees Celsius, which is 6 times hotter than the sun's core. High pressure. Pressure squeezes the atoms together. They must be within 1 times 10 to the minus 15 meters of each other to fuse. With current technology, we cannot achieve the temperatures and pressures required for deuterium-deuterium fusion. But deuterium-tritium fusion is possible. However, the former is the better option because it is easier to extract deuterium from seawater than to make tritium from lithium. The main application for nuclear fusion is in generating electricity. It can provide a safe, clean source in the future with several advantages over current fission reactors. There is essentially an unlimited supply of fuel for fusion since deuterium can be extracted from seawater. In contrast, uranium for fission is rare and must be mined and enriched before use in the reactors. The process of nuclear fusion is actually very clean. No combustion occurs during the reaction, so there will be no air pollution. This would be extremely beneficial given the current state of global warming. Another advantage that fusion reactors have over their fission counterparts is that they do not produce high levels of nuclear waste, so disposal will be less of a problem and it is generally much more safer. Nuclear fusion is actually very clean. No combustion occurs during the reaction, so there will be no air pollution. This would be extremely beneficial given